because my internet is being a little unstable here. So with that, thank you for joining us this evening for our 7th session of the Journey Down the Clackamas. I'm Dave Bugney, and board member of the Clackamas River Basin Council, or CRBC, and our family lives out here in rural Estacada. Joining me tonight are Todd Bartlett, CRBC Board Chair-elect, and Liz Gilliam, CRBC Restoration Program Manager, who will assist me in the technical aspects of administering this webinar tonight. Before we get into our program, I want to cover a few items. The CRBC is celebrating our 25th year anniversary. So since our founding in 1996, the CRBC has worked as a non-governmental group of stakeholders to protect and improve the Clackamas River Basin and its tributaries. Our mission is to foster partnerships for clean water and to improve fish and wildlife habitat and the quality of life for all those who live, work, and recreate in the Clackamas River Basin. On behalf of the Basin Council, I'd like to thank our gold sponsor, Clackamas Water Environment Services, or WES. We also thank our bronze sponsors, Clackamas River Water Providers and the Geological Society of the Oregon Country. And also thanks to all the many individuals who have donated to support this conference. We continue to seek additional donations, which are fully tax deductible. The Clackamas River Basin has been occupied by Native peoples for millennia. It was originally the territory of the Clackamas, the Chinook, Walla, Kalapuya, and other peoples, and is currently recognized as lands of the Confederated Tribes of Grand Moran, Confederated Tribes of Warm Springs, and belongs to other Native peoples who may not be federally recognized. We thank those who came before us for their stewardship of these lands and who continue to steward them now and in the future. We are gathered for this journey down the Clackamas to learn in-depth information about the basin and its connections to Oregon as a whole, to connect with each other so that we can support our mutual efforts to protect and improve the Clackamas River and its tributaries, and to have some educational fun all at the same time. The CRBC is partnering with the Environmental Learning Center at Clackamas Community College. Workshop attendees will receive CCC continuing education units and can also request a signed certificate of completion for each session. So if you'd like a certificate of completion, just add your contact information to our Journey Down the Clackamas Conferencing Networking Google Sheet. And if you'd like a certificate in the G column, we'll forward you the contact information to Clackamas Community College. So I'd like to share a few quick ground rules before we introduce our special guest for tonight. Please keep your microphones on mute unless invited to participate. And you can keep your cameras off if you like. That will help us save bandwidth for our presenter and greatly reduce the carbon footprint of our meeting. We will have 3 presenters this evening with a brief Q&A after those 3 have presented each of their topics. So please keep your, please type your questions in the chat box, and then we'll select the questions from there to try to get, group common questions. Feel free to send direct chats to friends if you're seeing them in the participant list. Now we'll start our presentation for this evening. Please remember to type your questions in the chat, keep yourself muted, and we'll answer questions after the presentation. So due to the amount of material to be presented, this webinar will extend to probably between 7:30 and 7:40 with questions afterwards. So tonight our presenters are going to be, first off, Dr. Max Nielson-Pincus, and he's Associate Professor and Chair of the Department of Environmental Science and Management at PSU. He received his BA in Economics from U of O, an MA in Environmental and Community Studies from Antioch University, and a PhD in Forestry from the University of Idaho. Then Dr. Loikith is an Associate Professor in the Department of Geography at Portland State and Director of the Portland State Climate Sciences Lab. He received his BS in Meteorology from Rutgers and an MS and PhD in Atmospheric Sciences also from Rutgers. And lastly, but not least, Mr. Chen is a second-year PhD student in the Earth, Environment, and Society program at PSU. He obtained his BS in Environmental Science from the University of Portland and his MS in Geography from Portland State University. So with all that, now let's welcome Max, Paul, and Junji as they present about weather, climate, and water in the Clackamas River Basin. Thank you.
Great. Well, thank you, David, and thank you, Liz and Todd, for organizing, and everybody who's here tonight for being here. So as David said, I'm Max Nielson-Pincus. I'm an associate professor and chair of the Department of Environmental Science and Management at Portland State University. And actually, I guess what I should do is share my screen so that it's sort of obvious what we're going to do here. So give me 1 second. Hopefully this will work. And somebody just give me a thumbs up if you can see my screen now. All right. Okay. I saw the thumbs up. Okay, so I'm going to start with an introduction. This is work that that Junji and Paul and I are going to present from a project that we called the Clackamas Watershed Resilience Project, which was what we think of as an interdisciplinary partnership model for conducting climate impact assessment. This is a photo of a group of us from Water Environment Services of Clackamas County, the Clackamas River Water Providers, Portland State University, and a few others at one of the treatment plants along the Clackamas drinking water treatment plants. So let me just go to the next slide, introduce who the players are in this. The three of us are going to do our best to represent all of these vast array of folks from Portland State, from the Institute for Sustainable Solutions at Portland State, from Water Environment Services and Clackamas and the Clackamas River Water Providers et al., who all contributed to this project. I'm here today to specifically give introduction and some overview and motivation for the project, talk a little bit about water in the Clackamas, about climate change, about our research project and our team and research goals. And then we'll get to some findings. What did we learn from the work that we did? And here's where we're going to go a little bit backwards. Due to other conflicts that I have tonight, I'm going to present both that motivation and the research project first. And then we're going to start with some impact. So I'm going to operate on behalf of a couple of my students. So Andy McAvoy, who is a Master's of Science student who graduated a year ago and now works for the Forest Service, as well as Aaron Upton, who is a PhD student that I worked with, who now works in the Portland area as a consultant. Both of them contributed to this project heavily. And so I'm going to present some of their work since they weren't able to be here tonight. And if you hear some background noise, my kids just walked in the door. So you might hear that here in a second. After I'm done, then Paul's going to pick it up with some of his work on the climatology of the Clackamas, and particularly looking at climate change and assessing climate change in the future in terms of, if I remember correctly, precipitation and temperature. And then June's going to finally bring it home with some of the look at flow and water quality in the Clackamas and under projections of climate change. And then Paul and June will end it off with hosting some Q&A and some discussion with you all. So with that, I just want to start with a little bit of background and context. So let's think about drinking water in the United States. So I know this is a really big picture, zoom out here, but in the United States, more than 210 million people rely on surface drinking water from rivers and streams. That's about 2/3 of the population of the country. In Oregon, we're actually a higher percentage, about 3/4 of Oregonians rely on surface water for their drinking water. And if we live in the Clackamas River Basin, you're exactly the same. You rely on that surface water for your drinking water, municipal water, industrial water, all that kind of water. It all comes for us out of the Clackamas. And so here we can see that in Oregon, Oregon's public surface drinking water systems are represented in the map on the left here with those sort of bluish purple polygons. So basically what you can see here is that out of all of the communities in the Willamette Valley and in Southern Oregon, basically everywhere that abuts up to the Cascades or is on the leeward side of the Coast Range is dependent on that snowpack that we get every summer. Or every winter to melt off in the summer and keep us through the rest of the year. And so here we are, we're going to look at the Clackamas. In the case of the Clackamas, we've got communities that are in the Clackamas Basin that depend on drinking water, and we got communities outside the Clackamas Basin across the Willamette River that depend on the Clackamas for drinking water. Approximately, if I remember the numbers right, about 350,000 people depending on the Clackamas River watershed for their drinking and other municipal domestic water sources. And at that drinking water watershed, or that domestic water source of the Clackamas River watershed, has lots of different uses in it, right? So we've got, and we all know this isn't a surprise, but we've got timber, we've got agriculture, we've got Christmas trees. We depend on it for recreation and fishing and all sorts of other things. We like to live near and be able to see the river as well. And so these are all things that begin to interact with that watershed in the provision of our drinking water. The Cascades are, have a mix of the Western Cascades and the High Cascades, which tend to shed water at different rates. The High Cascades absorb water through the snowpack and the porous rock that we have up in the high mountains. The Western Cascades are an older geology. They tend to shed water faster, and you get images like the one here seen from the Mackenzie River. We could certainly find a confluence on the Clackamas that looks similar to this, where Deer Creek here is coming in, bringing that sort of more turbid water from those West Cascades, whereas the High Cascades water is filtered through the ground, brings that clear water down to us here in the valley bottom. The Clackamas and the Mackenzie are two particularly important waters or river water bodies to the flow in the Willamette River, particularly in summertime. And so you can see in the graph in the bottom, this is August flow in the Willamette River, sort of during low flow periods. And you can see where the sources of water are. So they're really primarily coming from the Mackenzie, the Santiam, and the Clackamas, which bring those sort of jumps in the flow of the Willamette as it moves downstream. So particularly important to us down here in the Portland metropolitan area. Wildfire. I probably don't need to say much more. When we put this slide presentation together, these were our two sort of benchmarks to go off: the 36 pit fire in 2014, and then the Eagle Creek fire, which didn't burn in the Clackamas, but nearby, right? And we all know that that has changed dramatically in the last year as we experienced the Riverside Fire and many others. And so the Riverside Fire, which ignited on September 8th of this year, burned approximately 138,000 acres, resulted in evacuations, property loss, community impacts, forest impacts, too many to name in one place. And it was part of a set of synchronous fires along the Western Cascades that all happened at the same time under the same conditions. And you can see them presented here, and some work that Andres Holtz, who's a part of this team, and I and some others at Portland State University are working on to map fire severity. And quite a bit of the Riverside Fire, as well as others you can see burned at a high severity fire. Riverside Fire being the top left little polygon up in the top there. So these are the kinds of things that we have to manage for when we're thinking about water and particularly climate change. So let's talk about climate change for a second. So the 4th National Climate Assessment came out a few years ago. Volume 2 in that climate assessment assessed impacts of climate change risks and adaptation in the United States. And particularly within the 4th National Climate Assessment, they went into regional impacts. And so we see this sort of central challenge for planning for a more extreme future. In the Pacific Northwest, the regional impacts identified around water had to do with water quality and quantity. Things like increased air and water temperatures that increase water temperature, reduced snow to rain ratios. So that ratio of the amount of precipitation that falls as snow or that's falling in the West Cascades versus the High Cascades may be changing. More frequent and high intensity rainfall, and those higher temperatures, both air and water, combined with some other factors leading to potentially more freshwater harmful algal blooms too. So these are the types of things that we're sort of thinking about. How do we manage for in the context of increases in these things in the future? The 4th National Climate Assessment talks about adaptation strategies. With respect to the Pacific Northwest, it says, and I quote here, "Very likely that proactive management will be required, yet only medium confidence that adaptation will actually reduce the impacts of climate change here." And in many parts of the Northwest, the lack of redundancy within our infrastructure systems will limit our adaptive capacity. And to some extent, we can think about this in the Clackamas, where we have a sole source of drinking water, and therefore not a lot of redundancy in sort of what happens if we get a particularly bad year. Speaking of particularly bad years, 2015, this question at least a couple of years ago is, will this be a new normal? And the 2018 National Climate Assessment actually addressed this to some extent. 2015 was the Northwest warmest year on record. Most precipitation fell as rain instead of snow. We had record harmful algal blooms. We had some of the driest fuels and largest wildfire season on record. That was before last year, by the way. And record high temperatures in the lower Columbia and its tributaries. In 2015, we saw air temperatures relative to that 1970 to 99 average that were up about 3.5 degrees on average Fahrenheit. But what was most notable was those wintertime temperatures that were up nearly 6.2 degrees average or during the winter. And you know, the National Climate Assessment suggests that these kinds of conditions may be illustrative of what normal conditions in mid to late century should be. And what you see here on the right is just a assessment of April 1st snow water storage, so snow water equivalent. And this is from the Mackenzie Basin based on some research out of OSU. And what you see in the green line is 2014, and the y-axis here is elevation. The x-axis is snow water storage. And so you see you get a lot of snow water storage, particularly at high elevations. The median here is the gray line just to the left of the green line. I know there's a lot of gray lines there, so bear with me. But this is 2015, right? So we see a little bump in snow water storage above about 1,500 meters elevation, but not nearly what we see on most years, or even, you know, decent years or better years up here. And perhaps most notable is just the lack of snow water storage at all above, well, up to about 1,200 or close to 1,500 feet of elevation. So that's some of the context that we're sitting in thinking about what might the future bring. At the same time, my lab through the Portland State University prior to, well, around 2015 and somewhat prior to that, had engaged in some social science to look at stakeholder attitudes and perceptions in the Clackamas River. And it's both in the Clackamas River watershed. So we did a survey of landowners and their perspective on watershed stewardship programs. We also had done a survey of drinking water customers and their perspectives on source water protection. And this sort of sets some of the context for how we might think about adaptation in the future. So first, we know that from the landowner perspective, that they're landowners, there's a certain degree of trust and knowledge and need for technical assistance for certain organizations, some better than others in terms of trust. A certain amount of knowledge that exists in the watershed, and some places that are fairly amenable to engaging in sort of stewardship programs that might be amenable to adaptation. On the ratepayer side, we saw that about 75% ratepayers in the Clackamas Basin, this was in 2016, thought that climate change would threaten their water supplies. And 90% were supportive of source water protection programs. And the majority said they'd even be willing to pay at least, 50 cents a month, which I know, on their water bills to help adapt to climate change. And 50 cents may not sound like a lot, but when we start talking about 200,000 customers, you're starting to get into money that may be able to support or at least supplement existing adaptation programs. Not to say that this is what the Clackamas River Water Providers is intending to do, but it's at least a modicum of support. So here we are in the Clackamas River watershed. You can see the watershed represented there on the left. At the bottom of the watershed, we know is the Portland metropolitan area, particularly those communities within Clackamas County that receive their water from the Clackamas River watershed. We have a middle section here that's primarily a mix of industrial and non-industrial, agricultural and rural residential areas. And then our upper section of the watershed, which is actually the lower part of the map here, the most southern part of the map, which is the Mount Hood National Forest, which is comprised of a number of things, but a wilderness among them, national scenic rivers, as well as what the Forest Service might call matrix lands that are used for timber harvest and production. So the questions that we had were to understand how might precipitation patterns change in the future? How might extreme events change in the future? What about that snow rain? Is that likely to change? How about turbidity in the river, which affects domestic water provision, among other things? What about flow and flooding? Wildfire risks, how might those change in the future? And to use that information then for a framework for understanding risks and understanding stakeholders and their perceptions of those risks, what the vulnerabilities are, and therefore how we might adapt to that change. So if I didn't have to run here, I would just turn it over to Paul and say, let's go with the climatology, and let's start at the top of this list and talk about precipitation and extreme events. But we're going to go a little bit out of order. So I'm actually going to start at the bottom of the list and talk about wildfire risks. And then I'm going to talk a little bit about our stakeholder work. And then Paul's going to take it over with the climate predictions or the more basic climate science. Oh, I forgot we had one extra slide here. We'll just jump through this. Yeah, I've already explained it. So this is some work from Andy McAvoy. Andy was a graduate student here at Portland State University in the Master's of Science and Environmental Science Management program. And his work and his thesis focused on future wildfire risk in the Clackamas River watershed. And what he did was some modeling, and some of this was actually, this title slide was created when he only had preliminary results. We've updated it since then, but he modeled future fire activity between 2040 and 2069. And the results of his work are actually published, and I can put this in the chat when we're done here, in a paper in a journal called Fire, called Projected Impact of Mid-21st Century Climate Change on Wildfire Hazard in a Major Urban Watershed Outside Portland, Oregon, USA. And it's free and open access, so if anybody is interested in learning more, they can go to it. So this is a little bit of the kind of process diagram of what Andy did. He started with trying to understand what the kind of landscape conditions in the Clackamas watershed are, weather conditions, historic fire conditions. He then used what we call a FSIM. It's a large fire simulator that was developed by the Forest Service through their Missoula Fire Science Lab to develop a baseline model of potential fire risk in the future. He then calibrated that model based on existing fire data that we know, so that the model basically ended up predicting the types of fires that we see in recent history in the last 30 years or so. What Andy then did was worked with Paul and one of Paul's postdoctoral fellows to pull some data out of some modeled climate scenarios. And you kind of see those over here in the right. And so there was a bunch of different climate models that produce different projections of climate in the future. And you can see all those listed in there. And there are a bunch of letters that probably don't make a lot of sense to you, and they don't honestly make a lot of sense to me, but I know they mean something in terms of the type of the model that it came from. What we did was we pulled basically some of the results of those models that came from the sort of pushing the edges of the envelope. So we wanted to look at, well, let's look at the model that gives us the hot and driest outcomes, the most hot, most dry outcomes. Let's look at the model that gives us the most wet and most warm outcomes. And then let's look at a couple of intermediates. And we use that information then to run that calibrated FSIM model that was based on and was producing sort of what current fire simulations look like, to produce simulations of about 10,000 statistically plausible fire season based on each of these climate scenarios for the future, for that 2040 to 2069 time period. And where did I go here? Hold on one second. Lost myself on the screen. Okay, so what do we find? We don't need to spend too much more time on the method. So what do we find here? So first of all, we use a metric called energy release component. Energy release component is essentially is what you see represented in those fire danger signs. So we can correlate energy release component to what's on the fire danger side. The more extreme, the more towards that red of that little dial on the fire danger sign, that basically means the higher your energy release component is, which is the more productive a wildfire can be. In terms of productive is probably a bad word, but the more it's efficient at actually being a fire, right? And so then we basically modeled those different colors on the fire danger rating scale. So the oranges or the yellows, the oranges, and the reds. which we call the 80th, the 90th, and the 97th percentile fire weather, or ERC conditions. And so what you're going to see here in these first two panels are the hot and dry scenario. So if we go back to the previous slide, that's that hot and dry scenario over here. Hopefully you can see my cursor that I'm kind of circling around, that hot and dry scenario here. And then the warm wet scenario over here. Thanks, Todd. And so what we see in the red line then is under the Hadley climate model, that most aggressive climate model, is the change in ERC values over the course of the year from January to September. And what's obvious and notable here is the increase of that red line relative to the black line, which is our 30-year baseline, looking from 1970 to or 1980 to 2009, something like that. I can't remember exactly which period he used. And the numbers that you see along the x-axis are the number of days additional above that moderate, high, or extreme fire danger rating. So under this Hadley, well, we call it HADGEM model that's here, we had 29 additional moderate fire weather days, 43 additional high fire weather days, and 62, almost 2 months of additional high fire weather days under this particular modeled outcome. And as I'm sure Paul will tell you, it's important that we do, we look at these in sort of an ensemble framework. We didn't quite do the full ensemble model, but we took the bookends to just sort of give us a sense of what the range is like. Because as you notice in the next one over here, in the MIROC 5 model, we see relatively little change, right? There's an increase in springtime ERC values, but that tends to be a time of year when relative humidities and precipitation are greater. Maybe not this year so much, but most years. And so that leads us to actually an increase, a few day increase, about a week increase in moderate fire weather, but decreases actually in high and extreme fire weather. And so I kind of look at this as sort of the no change scenario, the best case scenario that we might come towards. And keeping on moving, then we look at our other two. These are our other two models. They're sort of moderate case models. In both cases, you can see pretty substantial increases in the number of high and extreme fire weather days. So basically 3 out of our 4 models on those bookends here are showing pretty big increases. We see some increases in the CRNM CM5 model, particularly in January through about June. So you can think of that as warmer winter and springtime temperatures. Not so much different in July and August, but then as we get August into September, October, we see that big increase in the shoulder, and our other model looks somewhat similar. So here we see about a month of additional extreme fire weather, and particularly some of that increase coming in the late season fires, September, October season fires, and which is pretty much exactly what we experienced this past year. Just to put a few numbers to it, what it all means. This is the first column here is the first row here is our baseline. That's our calibrated baseline model. It shows us that on average, every given year over the last 30 years or so, burned about 1,600 acres. So not a ton, but that on average, and then the second column shows our approximate max fire size. So this is running those fire models 10,000 times, let's see what the maximum looks like. And so we see a maximum of about 64,000 acres, even under the baseline. Now, we can look back now that we've been through 2020 and recognize that this model apparently was way under parameterized because we just experienced a 150,000 acre fire in 2020. Which is, fairly close to what we see in this HADGEM model, our most aggressive hot dry model, where our max fire size is about 124,000. So on average, models predict about doubling of fire activity to an increase in magnitude of acres burned each year in the watershed. So certainly something to be, something to look more into and to be concerned or aware of. We just then also look spatially in the watershed to see where different things are happening. So here's our baseline model. You can see the lighter or the greener and then the orangey and red colors show higher probability of places that'll burn in the watershed. And we can then look at it by each of these models as well. Not surprisingly, the upper watershed is where we see the most fire, the most likelihood of fire. But I think what becomes really interesting here is as we look at the change in that burn probability, we start to see some areas here, and these are looking at our 4 models relative to the baseline model. We see some increases, some specific increases in the lower watershed that were, I think, a little bit unanticipated. We expected some of these higher watershed increases to be relatively greater magnitude. But seeing the lower parts of the watershed have greater likelihood of burning in the future was a little bit of a surprise. And I think one of the interesting pieces here is that there's pretty good consistency across all these models that serve our bookends of the ensemble of climate models out there that suggests that the lower parts of the watershed may experience future higher burn probabilities. So that's our fire work, which leads us into the part that I would normally do at the very end after we said, well, here's all what we found, which is to say, so what did the stakeholders we talked to think about this? But I'm going to go forward with it anyhow. Hopefully that's okay with Paul and June. So these are stakeholder perspectives on climate risks and adaptation. This is Erin Upton's work. Thanks, Paul. Erin Upton's work, who was a PhD student and now a consultant in the Portland area. And what she did was she did some what we call qualitative research. So she reached out to stakeholders from a variety of different organizations to really just understand their perspectives on climate change, climate adaptation, and the risks and vulnerabilities. So she asked questions about the biggest threat to water resources, about stakeholder engagement and addressing those threats, and about adaptation, both opportunities and barriers to adaptation to climate change. And you can see an assortment of the different organizations that she talked to representatives of, and there were quite a number more than just these that are listed here. So these interviews were conducted in 2017 and 2018. When we looked at biggest threats, urbanization and development combined with climate change risks were some of the things that came up the most commonly across all of the stakeholders that Erin talked to. Looking at engagement, there was a desire, there was a recognition of the partnerships that were already being built. And I think this conference is really fascinating because in some ways it's an embodiment of the potential of all those partnerships that exist in the Clackamas. And so there was a recognition of the partnerships that were already existing within the Clackamas among organizations, among stakeholders, among residents and interested and engaged citizens, as well as some of the decision-making bodies in the county or in the watershed. But there was also a desire for more, and engagement and desire for engagement around climate adaptation and water resource resilience planning. So I'm glad we could be here for this. There's also, I think, across the board, we saw increased a need that people highlighted for increased education, particularly for elected officials, and then particularly science communication, where we can take the learning from science from organizations like Portland State and other universities, other agencies that are doing the science around the Clackamas and translate it to policy relevant solutions to inform the management and decision-making that folks on the ground are making on a day-to-day basis. The last part of what we did under the Erin's kind of rubric of the stakeholder work was a stakeholder workshop. So in May of 2019, we convened a group of almost 50 water natural resource planners, elected officials, scientists, and other engaged stakeholders to kind of talk about the results of all this work, both the work that I just presented from Andy, as well as the work that Paul and Junji are going to present in a moment, as well as others. And part of the outcome of that was to identify, you know, what are some of the adaptation opportunities for the Clackamas River watershed. And here are sort of the things that seem to bubble to the top. So new and larger wastewater, drinking water, and stormwater infrastructure, both opportunities for green as well as gray infrastructure. Alternative drinking water sources. So reflecting on that lack of redundancy, thinking about connections to other drinking water providers and sources, whether that be, I think there were suggestions that ranged from the Willamette to Interties being Portland, the city of Portland's water source, and the Clackamas as well, so that there was some redundancy and potential backup should a disaster happen. Thinking about alternative land management was another idea. And then also really, real interest in figuring out how do we do better consumer water conservation as well. And I think that is pretty much brings it to the end of what I have to say. And so with that, I'm going to turn it over to Paul to talk about the climate work. And I'll probably hang on for a couple more minutes, but then I'm going to have to run. So I apologize for not being here, but feel free to reach out to me. I'll put my contact information in the chat, and I'll post the link to that paper I mentioned in the chat as well. So thanks, everybody. I appreciate it.
Before you go, could you respond to the question about the difference between gray and green wastewater infrastructure?
Oh, yeah. Great question. Thanks, Gary, for posing the question. I just popped up the chat and go, oh yeah, I should have been watching. Yeah, gray and green wastewater infrastructure. We actually have a good example of it here in the Fernhill wetland complex, which is a constructed wetland complex over in Forest Grove that uses as tertiary treatment, or maybe it's secondary, I always forget, but it uses as part of the last part of the treatment process, constructed wetland system to filter and clean the water before it gets, in that case, dumped back into the Willamette River. It's an increasingly, what I would say is it's a tool of increasing interest. We both across Oregon, but also, I think across the country. We can see some examples of it in other cities around Oregon, like LeGrand and Prineville, both of which have added constructed wetlands systems to their wastewater treatment operations. So hopefully that's one way to describe the outcome. I'm sure there's others of you here who could probably talk more about it than I could.
There is one more question, Max, that maybe you could email us afterwards. There's a question if the data for the fire risk maps is publicly available.
That's a great question. I would reach out to me,
Okay.
whoever asked it, and I will, and we can figure out how to make that connection happen. Certainly, I'll send the link to the paper, and that way you can see what's in it, and then we can get a little more targeted. Thanks, Liz.
Great. Thanks, Max.
Yeah. With that, I'll stop my share.
All right. So I'll get started. Thanks, Max. Max, you did a great job sort of setting the stage and talking about the background on the project. And now I'm going to walk it back a little bit. As Max mentioned, we kind of mixed up the order of how we often present this. And I'm going to talk about the weather, the climate, climatology, and then climate change. I'm also going to talk about just the sort of basic physical, the sort of physical foundation for climate change as well. So some fundamentals. I think it's always good to kind of review those. So I'm going to go into the atmosphere now. I'm an atmospheric scientist, and so most of my research and my interest are around what's going on above the ground in the atmosphere. And then when I'm done, Junji will talk about what happens when rain falls out of the atmosphere and is on the ground and in the Clackamas River. So that'll be part 3. So I'm going to share my slides. I think I have more slides than I'll probably present, but let's see how this goes. And I thought we'd start out just really basic, something we're probably familiar with being in and from this region, but it's good to just kind of reflect on kind of how interesting climatologically the Clackamas Basin is. So Oregon in general is really interesting. I'm from the East Coast originally. You may have guessed that because my degrees are from Rutgers University in New Jersey. And you can go large distances across the East and still be relatively within the same climate zone. But because of the topography and the interaction with moisture coming from the Pacific Ocean In the West, we have much more complex and spatially heterogeneous climatology. And the Clackamas River spans a couple of different climate zones. And I just show this map here of Oregon's average precipitation, which is probably roughly familiar to us. We know it's drier on the east side of the Cascades and wetter on the west side. And here's the Clackamas River, and it starts in the kind of moderately wet Willamette Valley, and then it goes through a very wet kind of mid-elevation part of the Cascade Mountains, and it actually gets a little bit drier up by Timothy Lake and the higher elevations. So within the Portland metro, we have areas that get well over 130 inches of rain, not so much where the Clackamas River is, but certainly in the vicinity of it in the North Coast Range and in parts of the Northern Cascades. And then the the Willamette Valley more broadly is fairly moderate, with really half or even in some places a quarter of that precipitation. So only 30 to 40 inches of rain in the vicinity of the end of the Clackamas River. So when thinking about climate change and its effect on the Clackamas River, the first thing we kind of did was just kind of familiarize ourselves with the overall range of climate zones that the river is impacted by and travels through, because climate change will be different, or its effects will be different a little bit depending on where you're talking about. And then the overall drivers of this variety of climate zones, that's important as well. And I have this little cartoon that I quickly drew up. I think we're probably pretty familiar with the fact that the windward side of mountains in the west are rainier than the downwind side. But just to remind us, the reason why that is that when air rises, a parcel of air cools. And as that air cools, if it cools to what's called the dew point temperature, which is a measure of how much moisture there is in the air, the temperature and the dew point temperature reach the same value through the air temperature cooling, and then continues to cool, because as air rises, it does so, that air parcel must condense water vapor out of the air. So the dew point can't ever be higher than the actual temperature. So as the air parcel rises and it expands and it cools, it reaches dew point and continues to expand and cool. The dew point must decrease with the actual temperature. And anytime the dew point goes down, water vapor leaves the atmosphere. And in the case of the west side of the Cascades, that air is lifted as the wind comes primarily from the west, or some version of some westerly trajectory is forced up the Cascades, and it cools and condenses that water vapor out into clouds and into precipitation. And it can enhance precipitation. So that's why even when it's raining in the Willamette Valley, more rainfall is often measured on the westward side of the Cascades. So that's what drives the very wet climate. And then, of course, if you get high enough in elevation, or if the freezing level of the atmosphere gets low enough, then that precipitation falls as snow and frozen precipitation. So that's sort of the really fundamentals. The climatology of the Clackamas is really interesting around its precipitation and the range of precipitation zones that the river flows through. And then the seasonality of precipitation is also really interesting. This is also interesting to me as an East Coaster, where it rains basically about the same amount of rain every month of the year. But we know here in the West and in Oregon, we have a very seasonal climate of precipitation. So just to kind of visualize what we're already familiar with, this is the amount of rainfall that occurs, or rainfall equivalent within the Clackamas. This is at Clackamas Lake, so in the upper reaches of the river. Almost no precipitation in July and August, and lots of precipitation in the late fall and the winter. And then temperature is kind of the inverse of that. So the precipitation primarily falls when it's coldest, and it's warmest when it's dry. There's also very noticeable seasonality in snowpack at Clackamas Lake. So Clackamas Lake has a snowpack, snow water equivalent monitoring station, part of the SNOTEL network. And this is a chart made as part of the project that Max was talking about. So it's a little bit old. It ends in 2018. But what this just shows you is that the amount of water stored up in the snowpack, of course, has this annual cycle that peaks at the later part of the cold, wet winters, and then goes down to zero in the summer. And you can also see that if you look back, this goes back to about 1980 when the data started being available. There are stretches of years that had really low snowpack, stretches of years where it peaked at very high levels, and then everything in between. So there's a lot of variability from year to year in how much snowpack accumulates at Clackamas Lake. So this is showing us an average of the rainfall. Of course, this has been a drier year than average. Some years have been wetter, and then you can see the snowpack has a lot of variability. And here's that 2015 that Max was talking about. It looks like the data is missing there, but there just was essentially no snowpack that year. Greater than 80% of the overall precipitation in the Clackamas Basin, like much of Western Oregon, falls between October and April. I have this backwards somehow here, not April and October. I apologize about that. A quarter of the annual rainfall occurs in extreme events on average. That was something that we were able to tease out of the data. So 75% of the rain falls in kind of not extreme, just sort of moderate or light events, but a quarter of the rainfall occurs in the sort of upper percentiles of daily precipitation rate. I already talked about there's a lot of interannual variability here. And then as far as heavy rain and snow producers, the meteorological mechanism that's responsible for the majority of those are called atmospheric rivers, which I'll talk about on the next slide. They're a primary cause of heavy precipitation in the region. So they're an important weather mechanism. So this kind of just illustrates how important atmospheric rivers are. Atmospheric rivers are defined as long, narrow bands of large amounts of water vapor being transported through the atmosphere. So they need to be long, they need to be narrow, they need to have strong winds and lots of water vapor. So it's the river analogy in the name is, I think, pretty appropriate. It's a river of high amounts of water vapor being transported rapidly through the atmosphere. And remember, when air rises, it cools and it condenses that water vapor out in the form of clouds and precipitation. So when atmospheric rivers impact the Cascade Mountains and that moist air is forced upwards, then it results in oftentimes, not always, but oftentimes heavy precipitation. If it's cold enough, it will be snow. If it's warmer, it will be rain. And these are what atmospheric rivers look like from space. This is measuring the amount of water vapor in the atmosphere. They look like these filaments of high water vapor content in the atmosphere. Here's one that's making landfall just south of the Bay Area in California. These figures here are from some research that a PhD student of mine, Emily Slinsky, published, and it's just showing the percent of extreme precipitation events that can be attributed to atmospheric rivers across the Pacific Northwest, and then how common atmospheric rivers are. The top is for fall, September, October, and November, and the bottom is for winter, defined as December, January, and February. And the takeaway here, looking at these brightly colored maps on the right, is that these values here that are over 90% or near 100% in the geography that we're talking about, that means that over 90%, close to 100% of heavy extreme precipitation events can be attributed to atmospheric rivers. These maps on the left show that in fall and winter, atmospheric rivers are fairly common in the region as well, occurring about 10 to 12% of days in those seasons. So these are really, really important for those high impact precipitation events, but they're super important as well for water resources, snow accumulation, and those things as well. They can be important for snow melt if they're warm as well. So now let's switch gears and talk a little bit about climate change. That's just kind of the baseline, the background climatology, and the weather that's important here, mostly focusing on precipitation, a little bit on temperature. We'll talk more about temperature. But I always think it's important just to make sure we have our terminology right when talking about climate change. And so I wanted to quickly just go through some terms that I'll be using. So anthropogenic just means caused by humans, right? It's probably a familiar word. We talk about climate change in this context, we're talking about anthropogenic climate change that's forced by human activity. Global warming is sometimes used synonymously with climate change, and I think that's generally appropriate. But I like to think about global warming as the global scale. I mean, the term is actually really quite descriptive. The global scale warming that results from increasing concentrations of greenhouse gases in the atmosphere, whereas climate change is kind of the result of global warming. So the overall warming of the global climate then causes other elements of the climate change, or the climate system to change. So changes in rainfall or changes in local temperature are kind of climate change, but they're ultimately driven by that global warming. But the two terms kind of refer to the same thing. And we're talking about anthropogenic in both of these cases. I won't get into the difference between weather and climate. That's too much. It's of course really fundamental. Weather is short-term, climate is a long-term average of weather. And that's an important distinction as well. So I want to go through just a basic model of how the atmosphere works to illustrate how global warming can be caused by human activity. And this is really, really fundamentals of how the temperature of any planet arises. So we're going to do just a really simple, qualitative, descriptive model. We can apply mathematics to this, and you could plug this into a computer and change all these components and see what the response is, but we don't need to do that. We can do this really descriptively. So here we have the Earth's surface and the green line, and the sun here drawn not even close to scale in the sky. And the Earth receives energy from the sun in the form of relatively short wavelengths of energy. And that energy is absorbed by the Earth's surface, and then the Earth emits that energy in the form of heat proportional to its temperature in the form of longer wavelengths. So the hotter sun emits energy at higher frequency wavelengths, the cooler Earth emits energy back to space at lower frequency, but these two are balanced. So the Earth emits the same amount of energy that it receives from the sun. Now, in reality, it's a little bit more complicated than that. It's actually quite a bit more complicated than that. So the first thing to realistically add to this picture is the fact that 30% of what reaches the Earth from the sun doesn't ever actually go into warming the Earth's surface. It's reflected immediately back to space by bright surfaces. So mostly by clouds, also by ice and snow and other bright surfaces. So only 70% of what's received from the sun is absorbed at the surface. And then the Earth emits that energy back to space. And these would be in this basic model in perfect equilibrium, same amount of energy coming in as the amount of energy going out. Otherwise, that would not be physically possible. You'd have an infinite accumulation of energy if you weren't emitting the same amount of energy as space. And so this would be true for any object in the atmosphere or any planet in space. And again, the energy emitted by an object is proportional to its temperature, with a hotter object emitting more energy. If this model was true for Earth in its form that I have it here, the average global temperature would be -18 degrees Celsius. We could apply equations to this to prove this mathematically. Obviously, that's not true. The actual average temperature of Earth is about 15 or 16 degrees Celsius. So we are missing the atmosphere in this model. So I've included an atmosphere here in this blue rectangle. We have kind of all the other same elements, the energy coming from the sun, which the atmosphere is largely transparent to. 30% of that gets reflected by bright surfaces, primarily clouds. The rest reaches the Earth's surface and it warms the Earth's surface, and then the Earth emits that energy back to space. But because we have an atmosphere that's mostly nitrogen and oxygen, and those aren't important gases for this, but we have more trace concentrations of other gases highlighted in red, carbon dioxide, water vapor, methane, and others, that because of their molecular structure, they absorb some of this long wave energy, this heat energy that's going back to space. And so instead of the energy coming in from the sun, warming the Earth's surface, and that energy going back to space proportional to what it's receiving from the sun, a lot of that energy gets absorbed by these molecules in the atmosphere and essentially has a harder time making its way back to space. So a molecule will absorb some of that energy. These molecules are very effective at absorbing energy at the wavelengths that Earth's surface emits. And then they'll emit energy in all directions, and some of that will be absorbed by another molecule. Eventually, that energy does get emitted to space from a higher altitude in the atmosphere. And that higher altitude in the atmosphere is colder than near the surface. And remember, an object emits energy proportional to its temperature. So it's emitting energy at a lower temperature because this energy is eventually getting to space from a higher point in the atmosphere. What this does is it breaks this equilibrium. So the energy being received from the sun is not being balanced in time by the energy that's being released to space. You're having this accumulation of energy. So an object that needs to regain radiative equilibrium, as it's called, energy coming in versus energy going out, will warm in response to that because a warmer object now emits more energy. So Earth, in this case, warms in correlation to the concentrations of these gases in the atmosphere so that it can emit enough energy to space to balance what it's receiving from the sun. And that brings Earth's temperature up to a comfortable 15 or 16 degrees Celsius and allows life as we know it to exist on Earth. Anytime the concentrations of these gases change, and these are referred to as greenhouse gases because of their ability to warm the planet, anytime those concentrations change in one direction or the other, the global temperature will also change. So if the concentrations of these gases go up, the temperature will go up so that Earth can emit enough energy to balance what it's receiving from the sun. If they go down, the temperature will go down. Anything that actually changes this amount of incoming versus outgoing energy will change the global temperature. So what we're talking about with climate change is that human activity is primarily increasing the concentrations of this greenhouse gas, carbon dioxide, but also some others. And the carbon dioxide is really long lived in the atmosphere, so it accumulates like a reservoir, stays up there for extremely long time. And so its radiative effects are long lasting. And so there's a response in global temperature to changes in this gas. I think I'll skip the next slide, which goes into all the different gases and things in the atmosphere and what they do to global temperature. And just sort of start with some of the basics. We're not talking so much about the Clackamas Basin yet, although we'll bring it down here to the Willamette Valley just to demonstrate that it's both a local and global phenomenon. Here are the concentrations of carbon dioxide in the atmosphere. Again, once they get released through combustion of organic material, most problematic are fossil fuels because it's taking carbon that was stored in the Earth's surface, it was sequestered there, and it's liberating it into the atmosphere as a gas where it stays for a long time in that atmospheric reservoir. As those concentrations of carbon dioxide go up from that human activity, the temperature closely follows. Of course, there's lots of year-to-year variability here, but this curve of increasing concentrations of carbon dioxide started in the 1950s. So it's right about here when that started. Of course, the increase had been going on since the Industrial Revolution, but you can see that the temperature follows pretty closely. The red line, by the way, going up and down there, that's the seasonal cycle. This is measured at the very top of the Mauna Loa volcano in Hawaii in the free atmosphere. The northern hemisphere is a lot of forested and vegetated land. And in the wintertime, all that vegetation dies. It's made out of carbon, and carbon naturally increases in the atmosphere. And then in the summertime, and all the plants grow, they take that carbon back out of the atmosphere, make leaves and flowers. And so every season or every year you see the seasonal cycle, and that's what that red line is. That would exist without any increase in carbon dioxide. That's just a natural phenomenon. We can see here too that the increase in temperature in the Willamette Valley reflects largely the global increase, although every region in the world is a little bit different. The global increase is averaging all the regions together, but it's been warming by about 0.2 degrees Fahrenheit per decade as a result largely of this increase in concentrations of greenhouse gases. It's also important to note that the concentrations of carbon dioxide are effective at a global scale. They become well mixed around the world. That's why this is measured in the clean, free atmosphere. So local emissions of carbon dioxide don't disproportionately affect the climate of where they're emitted. So if they're emitted in Australia, if they're emitted in Norway, it affects Oregon's climate in the same way, just as if it's emitted in Oregon, it affects Norway or China or Antarctica in the same way. Okay, let's get more specific to our region. And so kind of zooming in towards the Clackamas Basin, these are some figures from the Oregon Climate Assessment Reports 4 and 5. So this is aggregated over the state of Oregon. And what this chart is showing in the blue and red bars is historical observations compared to a long-term average baseline, where the blue bars are cooler than that average baseline and the red bars are warmer. And you can see that we get warm years and cool years, and that's, there's warm stretches and cool stretches. But overall, we're seeing in the last couple of decades, more of these warm years, warmer than this average baseline than we are seeing cool years. And some of those very much warmer, 2015, 2018 were examples of that. And then everything to the right of these bars here, this shaded area, is our projections of future temperature averaged over the state. And this dark red line follows a scenario that is fed into a large range of climate models with different levels of sensitivity to increases in carbon dioxide. This is following a scenario of kind of unmitigated increases in carbon dioxide in the global atmosphere. And the yellow one is a scenario where about mid-century, the concentrations stop going up as rapidly and start to level off. And you can see either way, there's a lot of warming in the future, but the difference in those scenarios is a couple of degrees Fahrenheit. So about, on average, the models have about 5 degrees of warming, although there's quite a range. So some models only have a little bit more warming and others have a lot more warming under the mitigation scenario. And then the non-mitigation scenario, the balance of models, when you average them together, there are different sensitivities and assumptions is around 9 degrees. So that's not a forecast because we don't know what's going to happen with concentrations in the future, but it tells us what range of conditions we would expect compared to the historical baseline under these different scenarios of future changes in greenhouse gases. We can look at this spatially as well. So this is just a map showing projected change in days with a heat index above 90 degrees across Oregon. This is by the mid-21st century, so increase in several days in the lower Clackamas Basin. We'll look at that more specifically to the Clackamas Basin in a few slides. And then I show this map of the West just to show that summer sees a greater degree of warming looking into the mid-21st century compared to the historical climate than the other seasons do. So winter's warming at a slower rate, except in the mountains where snowpack is eventually kind of starting to be lost. That loss of snowpack will cause a disproportionate winter warming in the mountains, but generally speaking, summer is when the magnitude of warming is already and is projected to be the greatest. Okay, I'm going to skip that and just talk about a few other metrics and get to a few of the results from our Clackamas specific study as well. A couple of other interesting indicators of how things are changing across Oregon. This is specific to Portland, but this could be reflected regionally, so it's not just specific to the airport, these trends. This is a number of 90-degree or greater days each year going back to 1938. And again, like a lot of things, there's a lot of year-to-year variability. Years with not a lot of 90-degree days, 2018 that had the record. We had our first today in Portland by quite a bit, hit 95 in Portland. We don't know what this year will hold, but overall we have about 8 more days above 90 degrees on average in Portland than we did in the mid-20th century. So that's an indication of extreme heat getting worse. And this is a number of record warm days that were set in each year or are currently existing in each year. There's not a huge increase, but there's generally a tendency towards more record warm temperatures being set more recently. And if we look at extreme cold, it's similarly decreasing in severity. In fact, extreme cold severity decrease and warming of extreme cold is an even more robust sign of climate change globally and across the US and across Oregon in many ways than increasing heat. And you can see that we rarely break record low temperatures anymore in Portland. Most record lows were set in the mid and late 20th century. Precipitation is kind of a different story. These are just trend. This is looking at the long-term trend in precipitation for annual precipitation and for different regions in Oregon. And all that this says is that there's really no trend in annual precipitation. There are wet periods and dry periods, wet years and dry years, lots of variability, but so far to date, going back to 1895, there's no real systematic trend that we can detect in precipitation across Oregon. And that's true across a seasonal scale as well, with the top here being winter and the bottom being our dry season in the summer. Maybe summers are getting a little drier, but again, there's so much variability that noise is very high, so the signal is a bit hard to detect. If there is a signal, and I think there probably isn't really one at this point. Looking forward in time for precipitation, again, this is aggregated over the state here, just like we looked at for temperature, the light blue being the mitigation scenario, the dark blue not being a mitigation scenario, and both show very little change in average precipitation across the state of Oregon. And that's true across the different seasons. What this map shows is green means getting wetter by the end of the 21st century, brown means drier. But unless you have red dots, that trend is not particularly statistically significant. And if you have these diagonal lines, that means that the trend is very small compared to the overall uncertainty within the range of models. And what we see is that most of Oregon, except Eastern Oregon in the winter, doesn't have a really clear signal. And that fits this wide range of possibilities where the average kind of goes around zero. It is worth noting some models project things getting much wetter and some project them getting drier, but on the average, things tend to be maybe just a little bit wetter during our wet season and a little bit drier in the dry season, but average rainfall, it's fairly minor. When we look at extreme rainfall, which is really high impact, it gets a little bit more complicated. And again, remember, atmospheric rivers are key to our extreme rainfall. So it matters what will happen to atmospheric rivers for how extreme precipitation will change in the Clackamas Basin and elsewhere in the West. And there has been some research on this, and this is kind of a complicated graph that's illustrating the results. But basically what it's showing here, and this is actually by latitude, so we'd be kind of right around here somewhere. This blue line is how intense the top 1% of precipitation events from atmospheric rivers was in the historical climate. And by the end of the 21st century, the red line is the projections. And that's showing an increase in the most extreme rain from atmospheric rivers. But these dashed lines are the average rain, not the extreme, and those don't change too much. So a little bit higher intensity in the extreme rainfall caused by atmospheric rivers, but not an increase in the number of atmospheric rivers, not an increase necessarily in the average rainfall, but those extreme events getting a boost. And that's because a warmer atmosphere can hold more water vapor. So an atmospheric river that's really intense in a warmer climate can just have more water vapor that when it's lifted by the mountains or by some other lifting mechanism will rain more heavily. All right, specific to the basin, a former postdoc of mine, Dr. Ariel Catalano, she did some analysis, really high resolution climate models right over the basin. And this is for temperature on the left and precipitation on the right. We're looking at average temperature and average precipitation. The green line is the observations in the historical past. And then we have the pink line is the high-end emission scenario. The yellow line is the mitigation scenario. And this shows very similar to the state of Oregon, an increase in an annual average temperature in both scenarios, but of course, a greater increase with greater increases in greenhouse gases, although the two scenarios don't really diverge until the mid-21st century. Precipitation, very much like for the average of Oregon, is kind of all over the place with an average pretty close to not much change at all on average precipitation. That's not talking about extremes. Extremes in temperature for the basin, this shows the average frequency of days in the basin above 90 degrees. Of course, this is going to vary depending on what elevation you're at within the basin, but overall, the signal is very clear, they go up. But notice that in this high-end emission scenario, it goes up pretty slowly until about the mid-21st century, and then it takes off. And that's an important thing to note because I think a lot of attention is given to how much climate change or what kind of climate change we've experienced until today or what's happening now that didn't used to. But the magnitude of change that has happened in the past to today is rather small compared to what will likely happen in the future. So that's important to be aware of when making management plans and doing the kinds of things that Max was talking about, looks at. And then this is the average frequency of below freezing days, and they plummet already. There's not an increase in the mid-21st century, they just keep going down. So extreme cold or cold days are getting warmer, warm days are getting warmer as well, but cold's getting kind of disappearing faster. Lastly, I'll talk about snowpack. Ariel Catalano also did this really interesting work, and she published this as well, looking at projections of change in the freezing level of the atmosphere. So some research tries to simulate snow on the mountains themselves, and that's really helpful and it's useful. It's challenging though, because the mountains are very small and simulating the mountain topography in numerical models is computationally expensive. So we went a different route. And we looked at just where in the atmosphere is the 32-degree line, how far above or below the mountains is that, and then how does that change as the climate warms going into the future. And she looked specifically at the Clackamas Lake Snowtell Station as kind of a reference point. And so this graphic kind of illustrates that. In the historical past, the snow level was lower. As temperatures warm, it goes higher. And so below the freezing level, you have rainfall. Above it, you have snow. And as we go into the future, as the climate warms, the level of where the snow to rain transition is, on average, creeps up the mountain. And so you get more rain and less snow. And for Clackamas Lake, these histograms show how this changes, and it's kind of a busy figure. But what we're seeing here is the snow level for the historical record and in black here. So most often in the wintertime, so the peak of the histogram was about 3,000 feet. That's about where the freezing line historically is most often, although sometimes in the winter it's really high. And sometimes if you see -2,000 here, that means that the freezing level is technically way below the ground because it's below freezing at sea level. And then the blue line is the mid 21st century for that, and the red line is the late 21st century with the shading indicating the range of model solutions. And what this shows us is that that area where the freezing level is most often goes to the right, meaning it's getting higher. So the freezing level creeps up the mountain, creeps up the topography, and it's less likely to have the freezing level by the end of the 21st century below about 2,000 feet. It still happens in these models every once in a while, but way less frequently. So the proportion of precipitation falling as rain goes up and the proportion falling as snow goes down. Okay, that's, I think, everything that I have here. I have some references from the Oregon Climate Assessment Reports and the US National Climate Assessment Reports for further reading. There's a lot of good information there, and it's fairly approachable. So there's some links to that there, and those are really easy to find with a Google search. So I'll hand it over to Junji now, and then we'll take some questions with remaining time. Thanks, everyone.
Hi, let's see, I'm gonna share my screen. Can someone let me know if good? Okay, thank you. So my name is Junji. I'm a second-year PhD student at the Geography Department of Portland State University, and today I'll be kind of covering the last not talked about aspect of the Clackamas project that we did, which is climate change impacts on water quality and quantity. And this work is a collaboration with Paul, Max, and others. And the focus here, and this project is more part of what me and Dr. Hee-Jun Chang, which is also a professor in geography, did for our portion. So this project was split into two different phases. During the phase one, we dive into the historic pattern, look at historic data, and look at how extreme storm events in the past and what is their relation with turbidity and discharge peaks that we have observed historically in the Clackamas River Basin. And secondly, what are the possible sources? Where are the possible sources of sediment in urban and rural area along the Clackamas River, and how they are contributing to the peak in turbidity levels in the Clackamas after pretty intense rainstorms. And there was a paper that we published after phase one. I listed a little picture here. If you guys are interested, feel free to just Google the name and you'll find the paper that we published. And we also did a phase two. So for phase two, we approached our research questions by using modeling. So we try to understand the separate and combined impacts of climate. And this time we added in land cover change on streamflow metrics using a hydrology model called the SWAT model. And we also asked how might future climate change scenarios impact water quality at different times of the year. There's also a paper that came out of this phase two of the project. At the same time, this picture and link is posted here. for reference if you are interested. So these are kind of the overlook of our involvement in the project. And I'll start by going into our findings from phase 1, which mainly look at turbidity and discharge. So first, I'd like to just define turbidity a little bit. Turbidity is defined by the cloudiness of water caused by suspended matters, usually sediment. And then turbidity is one of the very important water quality indicators that indicates a river health. And I know there will be some pretty kind of busy graphics in this presentation. You guys don't need to look into too much about it. I'll try to help you guys to go over what the graph is showing and just come up with a takeaway that you guys can easily understand. So looking at the first graph over here, both of these graphs, they're linear regression graph. So pretty much what we're trying to do is to gather historical turbidity data and then compare that with discharge data as well as cumulative precipitation data. And as you can see over here, we have these linear regression lines that line up pretty well, showing a pretty high correlation between the two variables compared. And we found that the magnitude and timing of extreme storm events have a pretty significant impact on flow and sediment transport. And additionally, turbidity is also highly sensitive to intense precipitation and also elevated discharge as well. So those are kind of the takeaway we have from this graph. And why do we care about turbidity? In addition to it being a very important water quality indicator, high turbidity historically, especially with more days of high turbidity, correlate directly to higher treatment costs. As we all know, we take water from the Clackamas River and we treat it and we turn it into drinking water. So with more intense precipitation events, we get higher, more elevated turbidity level, increased treatment cost. And we don't want that, and that will just translate directly into taxpayer money. So our goal is to try to first observe what the relationship are and try to find ways to reduce turbidity levels by modeling and doing different types of research. And also historically, we also have observed discharge patterns in the Clackamas River. In December, kind of the winter month, we kind of categorize December flow as high flow. It's up 70% compared to the past century or so. And June flow, which we call kind of the summer dry low flow, it's down 16%. So that is not looking so good. We want lower high flow and we want higher low flows. And turbidity is strongly associated with these intense precipitation. So we believe that turbidity level may increase with higher high flows, and it may also increase in with respond to lower low flow due to the concentration of sediment in the river during low flow times. We also looked at peak turbidity timing, and we found that 60% of peaks of turbidity occur during extreme events. This is kind of expected. We expect that turbidity to peak during these extreme events, but we also found that turbidity tends to peak sooner, much earlier during a rainstorm in more urbanized and residential land covered area. So that's more of the downstream lower part of the Clackamas watershed. And also in the phase 1 finding, we were trying to look at the differences between upper and lower part of the watershed. That's more of urban agricultural versus the more forested upper part of the watershed. And we found that the turbidity pattern is highly influenced by land use gradient. So turbidity level is elevated much slower in the upper parts of the watershed and increase much faster in the lower parts of the watershed due to more impervious surfaces in developed area. So urbanization reduced the response time between precipitation and increased turbidity. And so therefore water quality kind of gets bad with the increased frequency of extreme storm, and it gets worse as you move down to the urban area. So now we're moving on to phase 2, which is heavily kind of model intensive. We used a hydrology model called the SWAT model. It stands for Soil and Water Assessment Tool. This model is a river basin scale model used to simulate water quality and quantity of water, predicts the impact of land use and land management practices, as well as climate change. And this model is also great for soil erosion assessment, non-point source pollution control, and also regional management in watershed. So here is a diagram, kind of a conceptual diagram of how this model works. So we have a couple of these climate variables that are inputs into the model. And we also have some land cover, characteristic variable data inputs for the model. And then the output of the model shows us the runoff quantity as well as water quality. And this model kind of requires calibration and validation using the historical data we already know and found during phase 1 of the project. So the results of this model, before I go into the results, there are certain structure of the model that I'd like to go over. So similar to Max and Paul's presentation, this is just slightly different. We kind of employ 3 types of climate scenarios, which are driven by 3 different climate models, as you guys previously learned. So we name them high, moderate, and low. And high represents the amplified climate change model. The moderate kind of represents the business as usual model, and the low impact, it's kind of the slow down climate change model. So in addition to that, we also selected 2 different future time periods for our models to run. So the first one we call the 2050s, which range from 2040 to 2069. And the second one we call it the 2080s, which range from 2070 to 2099, kind of the later part of the century. And we combined the 3 scenarios in a 2 time period, and we came up with 6 different land cover and climate change scenarios. So pretty much with these climate change and 2 time period, there's a data set out there called the Willamette Water 2100 project, and they provide a land cover map for each scenario that you define. So we found the 6 different land cover change scenario, and those are our inputs to our SWAT hydrology model. And we also divided the watershed into upper and lower part of the watershed, kind of split the Clackamas watershed into half, and then we will be comparing the differences between upper and lower part of the watershed. So first, these are the model output data. First, we looked at peak flow, which is concerning due to flood risk reasons. And we looked at the annual top 5% peak flow trend. And peak flow is also, if you guys remember from phase 1, it's highly correlated to turbidity. That's why we're interested in peak flow. And you can see that in the low impact and moderate impact scenarios in both the 2050s and 2080s time period, peak flow, annual average peak flow increased by more than 20% for these scenarios. So we can expect about 20% increase in peak flow under these scenarios, which may translate to some flood risk during winter and early spring time. And then we also looked at kind of the overall monthly average mean discharge for all these scenario. But instead of 6, we kind of just looked at the main 3, just the climate scenario by itself. And we found that the mean average monthly discharge is higher in all 3 scenarios compared to the recent historic, which is right here in the blue line. And then we found that in the low and high impact scenarios, the summer low flow during July, August, September for our future scenarios is lower than our observed historic scenarios. So again, spring and summer low flow is likely to decrease during these scenarios and may have certain implication for drought risk in the Clackamas. And we also looked at combined scenario as well. So in addition to climate and land cover scenario, looking at them kind of by themselves, we also look at the combined climate change and land cover scenarios. So we did that for a change in monthly mean flow. And we found that there is a higher change in mean flow during May to September than other months. and lower in the fall and spring month. And the upper part of the watershed, that is depicted in the bottom half of this figure, showed on an average slightly higher change, about 2 to 6% in monthly mean flow than the lower parts of the watershed. And the upper part of the watershed, of course, is more the forested area. A higher change on average flow is good. It's a good thing that we are expecting. So takeaway is that there is a hydrologic variability hydrologic variability is much higher in the lower part of the watershed, which is more urbanized and agricultural heavy. And this variability can lead to higher uncertainty when we combine it with the climate models and make predicting water quantity and quality with climate change much more difficult. So now we're looking at peak flow again, but across all 6 different scenarios, and we found that there's an increased peak flow in all climate scenario about 2 to 19% monthly. But we also found land cover change is more likely to decrease peak flow. So land cover change in the future will likely kind of reverse the effect of climate change. But when you combine land cover and climate change together, you look at a combined scenario, we'll still see that climate change scenarios dominates over the land cover change scenario. So that climate is still a primary driver for increase in peak flow. And then when we look at low flow, it's somewhat different. Climate change, of course, is still the biggest driver than land cover change. But in this case, land cover change does not reverse or mitigate the effect of climate change. It kind of exacerbates it. So both climate change and land cover change scenarios show decreasing trends in low flow, especially during the dry season when water demand is high. So here's some takeaways from the phase 1 and phase 2 project. Both precipitation and discharge are good predictors of turbidity events as expected, and the more rural part, upper part of the Clackamas watershed. But in the lower part, the more urbanized area, it's more complex. There's much more factors in the more developed area that causes different uncertainties and difficulties in predicting trends of turbidity. So there's more effort that are required in monitoring for turbidity, especially, and discharge at a finer spatial scale. So deploying more monitoring station will be beneficial to provide more data for this type of research. And looking in the future, the lower part of the Clackamas watershed has much higher hydrologic variability, and combine this with the variability of climate change, it may be the primary driver of diminished stream flow conditions in the future for the Clackamas River watershed. And also rising temperature and declining snowpack from climate change may also increase the discharge in spring and decrease the discharge in summer and dry season, threatening water supply. So we're expecting a much earlier peak of stream flow in the spring that may cause more flooding during the spring. And we're also expecting a lower low flow in the dry season. When people use more water, when the water demand is higher, we also get lower flow. So that is definitely threatening our water supply from the Clackamas River. And water resource in the Clackamas is also heavily driven by precipitation and snowmelt, and is highly sensitive to climate change from what we found in phase 2 of the project. Very sensitive to climate change signals than land cover change. So land cover plays a smaller role in the Clackamas River watershed than in climate change. Climate change is still the dominant driver of hydrologic changes and variability in our research. And lastly, uncertainties in climate models and the lower urbanized Clackamas watershed calls for improvement in model techniques and more efforts in data collection in the lower parts of the Clackamas. And that is my part of the presentation. Thank you all for coming today. And now we're going to spend some time on questions. Here is our contact information for me, Paul, and Max. Thank you.
Thank you very much, you three, for presenting tonight. This was truly in-depth and excellent, and hopefully filled in a lot of blanks for folks. So we'll open it up for questions. So Liz, you want to go ahead and go through there and try to collate the questions?
Yeah, not a ton of questions have come in. If anyone does have a question they'd like to ask and don't want to take the time to type it, you could also just type that you have a question in the chat or raise your hand, and we can unmute you, get you unmuted to ask that.
I see there is a question from Gary about humidity and heat, which I can answer. And it's a really good question. So I can start with that. So yeah, Gary, when it's hot in the east, it tends to be really uncomfortable and humid. And I have to remind myself of that when I complain about it being 95 degrees today. At least it's not humid, because if it was this temperature in New Jersey, it would be kind of unbearable. So the reason for that is that the amount of moisture in the air, or the source region for humidity in the air, is warm bodies of water or warm, moist places. So in the east, you have air that can pick up moisture from the Gulf of Mexico, which is really warm in the summer, air that can pick up moisture from the Western Atlantic, which is really warm. And you have a lot of rainfall in the summer in the east, so the land surface is also very moist, and that can supply moisture to the air. Now, warm air can hold more water vapor, so you actually have to put more moisture in the air when it's warm to make the relative humidity go up. So even in the most extreme humid heat waves in the East Coast, the relative humidity is probably about 40 or 45%, but it's the dew point temperature that's really important there. That's the measure of just how much water there really is in the air. And the dew point temperature can be like 75. Anything above about 65 is uncomfortable. And the West Coast, we have a cold body of water, the Pacific Ocean. So that's not going to give us a whole lot of summer moisture when the air is hot. And we have dry land, so we're not going to receive moisture off the land in the summer either. And the wintertime, having high relative humidities just means that the air is close in temperature to the dew point temperature. And so you have high relative humidity on actually when it's 15 degrees and snowing, the relative humidity is 100%. So it's just telling you how close the air is to saturation for that temperature. So here it tends to be cool and damp in the winter, and in the summer, the dew point might actually be higher than it is in the winter, but the temperature is so much higher that the humidity is very low. So I hope that answers it. Humidity is actually kind of a funny variable, but what we feel is that we don't have a warm body of water evaporating moisture into the air here in the West.
Thank you. Excellent answer. An excellent question. Chris Stanton asks if there is information online to help us understand which rivers are changing due to climate change. So more of a compendium of projected impacts on rivers across, a spectrum of geographies.
Yeah, Paul, do you want me to go ahead?
Please go ahead.
Oh yeah. So this is an excellent question. So for I don't think there is a website that will show you a spectrum of river changes and how they respond to a different climate change. But they are, for Oregon at least, there are different websites out there from different federal agencies such as the USGS, the U.S. Forest Service, and NOAA. They may have different types of research reports and perhaps maps that may show different aspects of river responding to climate change. For example, USGS will probably have information on how flow, discharge, and water quality responds to climate change, or different reports done in Oregon. The U.S. Forest may have information on how wildfire may impact water quality, and websites like NOAA may have information on how precipitation or climate change has impact on the river. So there isn't really a one big website that can answer your questions, but I can provide a list of these different federal agency websites that you can go on and kind of explore. Some of them have really cool maps that will show you, for example, stream temperature from the USGS and how they change over time in Oregon. So if you're interested, feel free to reach out to me to my email, and I can send you a list of these websites and where to find these interactive maps.
Yeah, thank you. I might reach out to you as well, and then we can provide some of those links onto the Journey Down the Clackamas website, so people know where to find those resources.
Liz, another thing I would mention is that the U.S. Forest Service has in their Rocky Mountain Research Station over in Boise, they're compiling through a geospatial statistical streamwork network analysis, water temperatures for the Pacific Northwest. And it's an evolving process right now. And that's one thing we're going to be doing is providing water temperatures to this data set so they can use that to project how climate change, given various climate change scenarios like we just expressed this evening, how those will affect the water temperatures given the database that currently exists, but it's sparse and it needs to be populated. And that's why we're going to be doing this large water temperature study starting this summer.
Yeah, thank you. David has organized a pretty big effort of getting a lot of water temperature data loggers out into the Clackamas River Basin, starting this summer for at least the next 3 years. There is a couple of more great questions that came in. Given the projected reduction in snowmelt water sources over time, are there any mitigation plans to increase water retention, or have we expended those opportunities to build dams and reservoirs? I don't know if you've come across many conversations about this during the course of the studies.
I don't think I have a good answer.
Yeah, I
Yeah.
don't think I answers that question. I don't
I'm
think
sure
we
it's
came
being
across.
thought about. We can see when PGE is going to be talking during the conference. When do you think we will start seeing the effect? When we will start seeing the effect of the fires, looking specifically at when turbidity will change, and maybe to what degree from the runoff as flora is largely gone along sections of the upper river? That's a great question.
Yeah, this is a great question. Actually, I'm working on that right now for my dissertation, but kind of still in the early literature research process of that. So from what I know now is that there is a immediate, so there are two different effects of wildfire and water quality, like turbidity change. Even though I did not dive into that in this project, Max talked about it briefly. We didn't really get an opportunity to connect the impact of fire to water. It was more separated for this project, but I'm planning to do that currently for my own research. What I'm seeing is that there's an immediate response to wildfire, and there's a long-term response of water quality to wildfire. So for the immediate response, it's more dependent on the weather. For example, last year when we had the wildfire from July all the way to October, what is the weather pattern like immediately after the fire? If we get really intense storms after the fire, it may wash off a lot of those burn debris and ashes into the river, and that can diminish turbidity level significantly immediately following the fire. But there's also a long-term effect, and the long-term effect of fire on water quality relies more also on the immediate weather pattern. If we don't get a kind of immediate storm events after fire, if we get kind of a dry, low flow winter, we may see turbidity response to be longer lasting, to kind of happen more over time instead of all at once after the fire. And there's also a lot of other factors too, such as fire severity, what types of vegetations are burned, because different vegetation may have different ability to hold the soil together. So there's a lot of different factors, but in terms of turbidity and timing, I think we will see probably a peak of much elevated turbidity level immediately after the fire. But the long-term effect, we still kind of have to wait on that to see, because the recent fires, like the 2019 and 2020 fire, is still kind of fresh, and it may take up to 5 years for us to see the long-term effect on turbidity, since the watershed is still kind of in the recovery process. Yep.
Thank you. Chris Stanton has a question, and let me know if I'm interpreting this right or not, but is there a general preference in scenario for river life? So is that the turbidity question, whether it is a prolonged increase in turbidity over time with lower precipitation immediately after the fire versus, a big storm and a big slug of turbidity all at once?
Ideally, the prolonged, when you spread out the turbidity increase over time is much better. But in Oregon, we also like to use this method called salvage logging, which is the removal of these vegetation after fire, like to salvage logs and different for wood. And salvage logging actually has pros and cons to the amount of turbidity level. So salvage logging, from heavy equipment, it may compact the soil, which can make it more hydrophobic and less likely to become sediment and that will go into the river. So that may be good for the turbidity. But at the same time, research recently have found that burned trees that are still standing or even debris on the ground, burned tree that are still standing and may actually have impact, may actually still have its ability to hold the soil and dirt together in the forest. So immediately when we don't, after the fire, when we don't salvage log, those burnt trees may still serve the purpose, maybe at a fraction of the efficiency as alive standing trees. So there are pros and cons of salvage logging, and that can definitely impact turbidity level. But in general, I think a preference, I don't think there is a general preference for turbidity level. We want to keep it, the lower, the better, whether that's immediate or over a long period of time. But I think it really depends on what type of management strategy in the watershed that will work best for the area that is burned.
Great. I have one more question for you. We're getting near the end of the questions in the comments, so keep bringing them in. But I was wondering about, I know a lot of your research focused on high flows and turbidity levels, but I was wondering if you looked at low flows and the timing or magnitude of low flows in the summer and how those change under these scenarios.
Yeah, sorry, is that Todd's question, or sorry, I'm reading the chat? Or
oh no, I just threw it out there. I
Oh.
didn't actually. That came from me.
Oh, okay. So sorry. I was reading that question. I thought you were reading it. Could you repeat it one more time?
Yeah, I was just wondering if you took a look at low flows in relation to water quality and the timing and magnitude of low flows in the river projected.
Yes, yeah, we did look at low flow, and I think that's maybe maybe I didn't show that. Yes, we looked at low flow in kind of the phase 2 of the project, although we didn't relate it directly to turbidity. That's more phase 1. So in phase 2, when we looked at low flow, we found that climate change and land cover change are both bad. They both reduce low flow already in the dry summer month. But unfortunately, we didn't relate that to phase 1 of our study. But we do know, and we're pretty confident that the model of climate change low flow results may cause a higher turbidity level in the dry seasons during the summer. When you kind of go back and compare that to the correlation that we found between magnitude of storms and turbidity. Sorry, I meant, so that's the wet season. And we didn't look at low flow that much in low season, but we expect that with less water in the river. So if you think about turbidity, like concentration of turbidity in the river water, with less water, the concentration is higher. So we expect low flow to actually diminish turbidity also and water quality just by concentration, by increasing the concentration of these sediment with the lower volume of water. We didn't look into it specifically, but I think that would be my answer to your question. We expect turbidity to increase during low flow times.
Okay. And then, yeah, sorry that I threw it out of order. One last question is, other than the great degree of variability in precipitation, are there theories as to why there are discernible trends in temperature but not in precipitation?
That's a really great question. And the sort of the existence of that difference in trends depends on where you are in the world, because there are places where there are discernible trends in precipitation. But generally speaking, the further you get away from the direct effects of global warming, the more variable the trend will be, or the harder to detect that trend will be, or it might take longer to detect because it's sort of a secondary effect. And changes in precipitation due to global warming can occur for two primary reasons. One is the water vapor holding capacity of the atmosphere. As it gets warmer, you can hold more water vapor. So all other things being equal, if they were all held the same, then you would have more precipitation. But you could also have changes in atmospheric circulation, so storm tracks and other things. And so these two kind of combine to determine exactly how rainfall or snow amount will change as a result of a warming climate. Here in the Pacific Northwest, I think a lot of the story is the high degree of variability, which makes it difficult to detect a trend. There's a large noise and a low signal. But the other thing is the mechanism that drives our precipitation may not be as affected by warming climate as quickly as other rainfall mechanisms. So like tropical rainfall, for example, is affected in a different way by warming temperatures than atmospheric river rainfall. And so we have very different dynamics. And as the climate warms and atmospheric rivers may hold more water vapor, that doesn't necessarily translate directly into more rainfall and in the region that we're in. So part of that is the shallow layer of water vapor in the atmospheric river near the surface, how it's lifted by mountains isn't as efficient at precipitation as really deep upward vertical motion and tropical precipitation. So it's kind of a complicated answer I'm giving, but the picture there is rather complex. So here in the Pacific Northwest, the increasing temperatures are a direct translation of global warming that's being experienced to some degree in greater and lower magnitudes all around the world. Changes in precipitation are sort of a secondary and tertiary climate change effect of that overall warming. And that's going to be manifested in different ways and at different rates, depending on the geography and the type of storm that tends to cause precipitation in a place. So we just happen to be in a place where that variability is high. And then because of the type of precipitation we get, the signal's quite low compared to some other places.
Thank you for a great explanation. Well, that's all the questions in the chat.
Okay, well, we might as well wrap it up then. So for those folks that need to log off, we just have a few announcements before we say goodbye. So hopefully just hang out another minute or two if you could. Our next session will be on June 15th. That will be Geology 6 with presenter Peter Wampler of Grand Valley State University. He'll discuss hydrology, geomorphology, and stream processes. So you can see now how we're getting a good understanding. We've gotten a good understanding of geology and a brief introduction to hydrology and climate. And now we're going to start applying that information a little bit more specifically to how rivers and creeks and other basins work. So you can use the same Zoom meeting link, and we're already you are already registered for the event. So we'll send an email reminder a day or so before, like hopefully you folks got today or yesterday. And then we'll send you a thank you email with these links, as well as a link to the recording and more information about getting continuing education units from Clackamas Community College. Again, our thanks to Paul, Max, and Junji for a marvelous talk. This has been months in the making, as we know, and Paul's done a great job. Paul, you're just amazing, and especially with all the work you folks have had to do, I really appreciate it. We also thank our gold sponsor, Clackamas Water Environment Services, and the bronze sponsors, Clackamas River Water Providers and the Geological Society of the Oregon Country, for helping us keep this conference free for all participants. So every little bit helps again, so please consider a small donation if you can. And thank you for joining us tonight. Please let us know what you thought of tonight's program, and hopefully we'll see you 2 Tuesdays from now on the 15th. Thanks
Thank
all.
you, everyone.
Everyone.
Thank you. Thank you.